Well, we're going to answer this question. This was question done in November in 2023 in the KZN province. It's a very good question I selected because of that. It's a good time to practice waves. This question says a section of the wave is represented below, and we have that section there. Let's first identify how many waves are represented there. Well, if you're starting from point A, from here, and you end at this specific crest, we have in there one wave. All right, remember, and that is also good time to revise this one. This point is called crest, and the lower point of the graph is called, or of the wave is called trough. That is an important point to remember now. Now from there, we have another part of the wave, which is not a complete wave. If you look here, we have half a wave up until there. Up until there, you have half a wave. And from there to B, you have half of a half. So in other words, guys, this part here that I just represent, let me just take a color to write that one there. This part here is going to be 3/4 of a wave. Only that part, only that gray part is 3/4. It's not a complete wave. So how many waves are represented in this specific part? Well, 3/4 is the same as saying 0.75 waves. All right, so the total amount of wave that we have here is 1.75 waves. We have in this drawing or in this representation 1.75 wave. It is important for what is coming now. All right, the frequency of the wave is 2.5 hertz. What is frequency? Just in case somebody don't have the definition, frequency is the number of wave that pass a point in 1 second. Point in 1 second. That is what we call frequency. It's an important definition. You never know if they're going to ask you to calculate frequency. And frequency is equal to 1 divided by period. So if you have the frequency, you may calculate the period. Period is the time for one complete wave. Okay. Question 2.1.1 is the above a transverse or a longitudinal wave? Well, guys, we have to just recall real fast. Remember, this is not a lesson, it's a solution of a question, but we're explaining some concept. Waves can be transverse or longitudinal. Or longitudinal. I moved down by accident. Longitudinal. I don't know why I draw a dot there. All right. Example of longitudinal, we have sound. All right. Example of transverse, we have water, waves. Those are examples of longitudinal and transverse simultaneously. Okay. Now, a transverse wave. When is a wave going to be transverse? When the particles moves, so that particles move perpendicular to the motion of the wave. All right, so in other words, if we have a wave represented, which I'm going to draw just part of a wave, that one is made of particles. You know that there are many particles. I'm not going to represent all of them, but those particles are moving up and down as the wave moves in another direction. For instance, those particles move like that. These are represent motion of particles. But this wave, it won't move up and down. It will move, for instance, let's say, to the right. So this wave can be moving to the right. Motion of wave. So that is a transverse wave. Now, longitudinal, guys, is when the particles move parallel to the motion of the wave. To the motion of the wave. That is when a wave is going to be longitudinal. For instance, if we represent a wave, remember in this case, we use lines to represent that specific wave, in which we have regions that are called compressions, and we have regions that are called rarefaction, but this is not the point right now. From here, you need to know that in this way, this is sound, for instance, the particles are going to move front and back. All right, this is motion of particles. But the wave is going to move also in that direction. So the wave, for instance, could be moving to the right. Motion of wave. That represents the motion of the wave. Guys, we just answer question 2.1.1. It is going to be a transverse wave. If they ask you justify or explain your answer, because the particles move perpendicular to the motion of the wave. Question 2.1.2, calculate the speed of the wave. It's simple to calculate the speed of the wave, and when you do this type of question, guys, get used to write the data. It's important. So data, not with a highlight, rather with a pen. So let's write here data. And this is question 2.1.2, if I'm not mistaken. There we go. So the data, what is known by us, what they gave us? Well, they gave us, first of all, the frequency, which is 2.5 hertz, if I'm not mistaken. I want to make sure it's a 2.5 hertz. We also have the wavelengths, and I'm going to show you just now in the graph. It's 0.3 meters. The wavelength is the distance between any two consecutive crests or any two consecutive troughs. The wavelength, by definition, is the distance between any two consecutive points that are moving in phase. So this one is the wavelength, and it's also given to you. It's 0.3. You're looking for speed. Straightforward. If you go to the formulas that they give you at the end of the exam, you'll get that speed is equal to wavelength multiplied by frequency. Straightforward, guys. Speed is equal to 0.3 multiplied by 2.5. The speed is going to be, let me just, 0.3 times 2.5, 0.75 meters per second. That is the answer. If you answer this first question, then you already get 1, 2, and 3 marks. It's quite simple. The next question may be tricky. Let's have a look. They say determine the time x between point A and B. The time x, how many waves are represented there? 1.75 wave. That is important. So the distance there is going to be, it's going to be a little bit tricky. So let's calculate the distance first, because that one is not one wavelength. All right. So what is the wavelength? And let's get the distance here. The wavelength is 0.3. It means from A to that point here, from A to that specific point, that one is equal to 0.3 meters. All right. But now from that point to the end, and I'm going to move that word of crest to this side here, so it doesn't get me disturbed of what I'm writing now. So from that point to here, what we have is 3/4 of 0.3, because 0.3 is one wave, and that is 3/4 of a wave. So this one is going to be equal to, and let me just write it, let me just calculate, 3/4 of 0.3, you get that it's 0.225. So this one is 0.225 meters. So what is the distance from A to B? Well, from A to B, the distance is going to be when you add all that. So from A to B, distance A to B is equal to 0,3 plus 0,225. All right, that is the distance, which is equal to 0,525 meters. I hope that is clear. It is tricky. My own learners struggle with that part to know, and they ask me, they look at the memo quickly and they ask the 0,525 where is coming from. So that is the distance from A to B. That is the addition of one wavelength, which is 0,3, plus 3/4 of a wavelength. That is why when we start working with this question, I recommend you to identify how many waves are represented as you will need it. There are other options to do this one, but I like this way. All right, so now we have the distance, we're looking for time, and we have the speed. So let's go for question 2.1.3, and I think it's going to be enough space here, guys. This is question 2.1.3. Let's write the data. Now what we have the distance, which is equal to 0,525 meters. We have the time, which is unknown. We're looking for the time, and we have the speed, which we calculated previously, 0,75 meters per second. We're looking for time. So what formula are we going to use here, guys? Well, if you go to the formulas, this formula is there. Distance or speed is equal to distance divided by time. And I'm going to write time with just a T for this specific topic. I personally recommend you to substitute like that. So the speed is 0,75, the distance is 0,525 divided by time. When you rearrange this one, you'll get that time is equal to 0,525 divided by 0,75. So you go there. The answer is going to be 0,7 seconds. That is the final answer for this specific question. So marking wise, let's have a look because it's important. It's also 3 marks. It's 1 for the formula, 1 for the substitution, and 1 for the final answer. I want you to pay attention carefully to this calculation I done here on top. You need to know the distance from A to B, and I'm going to repeat it once more. I cannot get stressed enough. From A to the first crest is 1 wavelength is 0,3. And from that first crest to B is 3/4 of a wave. 3/4 of 0,3 is going to be 0,225. When you add to 0,3, you'll get the distance from A to B. I hope it's clear. All right, and that one was question 2.1.3. Question 2.2 say, and now this one have to do with sound. Shapes use sonar to map and measure the depth of the ocean. There's a word there. Of the ocean at different points. This is achieved by emitting sound wave into the sea and determine the reflected sound or detecting the reflected sound. So how do it work? The ship send a signal to the bottom of the sea. That signal bounce, which is reflected, go back, and the ship detect that reflected sound. That is how it works. The principle of this machine. The sound wave emitted by sonar on the ship takes 0,8 seconds to reach point P. We're going to see the picture is here, and we're going to start writing the data there. So the sound wave emitted by sonar of the ship takes 0,8 seconds to reach point P. So 0,8 seconds. So the time here to reach that point P, guys, and we're going to write it here, the time here is equal to 0,8 seconds. Now, this is an important point. You cannot write sec. So for instance, when you write here, if you write sec, you lose the mark. That is wrong. You can either use the symbol S or you write the full entire word seconds. I think it's a good point to mention that one there. Seconds to reach point P, which is at the seabed 1,200 meters below the ship. You can see there, the data is given to you. Q is a second point on the seabed as shown in the diagram below. You have another shape and a point Q of the same shape, but you have a deeper point. Calculate the speed of sound in seawater at point P. Very easy. How do we calculate speed of sound? Using the same formula we just did. So data, and this is question 2.2.1. Data. What data we have? The distance that is going to travel that sound in the water is 1,200 meters. The time taken for covering that distance up until the bottom of the sea is going to be 0.8 seconds. And then you're looking for speed. You are going to use the same formula. Speed is equal to distance, which is 1,200 divided by the time, which is 0.8. You will get that speed is, and let me calculate, 1,200 divided by 0.8. Guys, you get 1,500 meters per second. Straightforward. 1 mark for the formula, which I did not write. Make sure you write the formula. I say it, and then I did not write it down. This one is distance divided by time, and all that is equal to 1,200 divided by 0.8, 1,500. That is the question. Marks, it will be 3 marks, 1, 2, and 3. It is estimated that the speed of sound in seawater increases by 4.5 meters per second for every 1 degree Celsius. They give you a new data here that I'm just not going to write. I'm going to highlight it. Increase by 4.5 meters per second for every 1 degree Celsius of temperature. The temperature of the seawater at point Q is 2 degrees higher than at point P. So the temperature at this specific point is 2 degrees higher. Now, if it's 2 degrees higher, for every 1 degree, it increases by 4.5. So if it's 2 degrees, it will increase by 4.5 plus 4.5, all right, which is 9. So it means that increases by 9 from P to Q, all right. The speed increases by 9. So speed here is equal to same speed, 1,500 plus 9, because it increases by 4.5 every 1 degree, but there are 2 degrees of temperature increase. So this is equal to 1,509 meters per second. That is the speed to reach point Q. All right. When sound wave is emitted directly above point Q, the reflected sound wave is detected 2.5 seconds later. Now, the reflected sound is the sound that went to the bottom, bounces at point Q, guys, and move all the way back. That is the reflected sound. We don't need that one. We only need the time to go down. So, for instance, time to go down and up is equal to 2.5 seconds. We need the time to go only down, because that is the distance we are measuring here. It's going to be equal to 2.5 divided by 2, guys. That one will be 1.25. So this one is equal to 1.25 seconds. That is the time. All right. We are looking for the distance. Determine the depth of the sea at point Q. So we have the data here. We have the speed. We have the time. We're looking for distance. Guys, we are going to use the same formula as before. All right. And I'm not going to write the data, is just written here. So speed is equal to distance divided by time. Remember, it's the time to go down only. The speed is 1,509. The distance is what we are looking for, and the time is 1.25. When you rearrange, you'll get the distance is equal to 1,509 multiplied by 1.25. So the distance here is going to be of the depth of the ocean at that point is 1,000, let me just write it, 509 times 1.25, that one is 1,886.25 meters. Guys, we are done. This question is fully done, if I'm not mistaken. Determine the depth. So we are done. 14 marks for this question. It's a lot of marks, guys. Marking wise is the same story. You get 4 marks. One of them is by calculating the speed here, one for the formula and substitution, and one for the final answer. Quite simple, guys. I hope it helped. If it helped, all you have to do is to thumb up to support the channel, and then Don't forget to subscribe. I'll see you next time with more Mr. G here.